So, very good evening to all the beloved members gathered here. I, on behalf of Pune Polytechnic, welcome you all to the third day of the webinar series on top tech trends. Today, we are privileged to have in our midst an Asian speaker and innovation master at Intel Corporation who has 3 decades of IT expertise, but also more inclined as a family mentor, and hence a man with perfect balance of technology and humanity. He is none other than Dr. Sundar Vedantam, Director of Software Development at Intel Corporation. Thanks for accepting our invitation in spite of your busy schedule, sir. We welcome you. Dr. Sundar will take us into the journey of 5G communication, highlighting its impact on businesses today. I welcome dear members of academia, industry, and the student participants who are joining with us through the YouTube link. I now hand over this session to our Dean, Dr. Mrs. B. Rajalakshmi, to introduce the speaker of today's session. Thanks, ma'am.
Thank you, Dr. Joshua. Okay. It's my proud privilege to introduce Dr. Sundar Vedantam. I would be reading out his short profile. Dr. Sundar Vedantam is the Director of Software Development working in the Data Center Group DCG of Intel Corporation in Allentown, PA. He is a lifetime member of the ACM and is involved in promoting the organization both inside and outside his company. I don't think Intel needs promotion, but still, yes. His skill set and experience cover a wide range of telecommunication-related domains. His team is currently involved in delivering highly optimized firmware layers that run on complex SoC, system-on-chip devices that power mobile networks. While the previously delivered software versions have been successfully deployed in 4G networks around the world, his team is currently working on the platform software layer needed for the forthcoming 5G deployments. He joined Lucent Technologies a couple of decades back and has traveled through various incarnations of his division as Ageri Systems, LSI, Avago, to eventually become part of the Intel Corporation. In the previous decades, he has worked on system integration issues related to DSLAM, RNC Node B systems, high-speed NIC, network interface cards for intrusion detection, and business system gateway designs. His research interests include network traffic and congestion management, high-speed networking, security, and theoretical computer models, areas in which he holds patents and has published papers, book chapters, and articles. He received his PhD in computer science in 1997 from Louisiana State University. In his early years, he has worked in a helicopter design bureau and served 2 years as a maintenance engineer in an offshore oil and gas platform. He enjoys writing articles in English and Tamil to help improve public understanding of the technical details behind the fields he has worked on and to attract young students to get into STEM fields. Many of his articles are available online for free. As part of this effort, he has published a book in Tamil, Thought Experiments, available on the web to help anyone from high school students onwards to understand complex ideas embedded in fields like mathematics, computer science, physics, ethics, democracy, and medicines. To add just a few words, there is a website called solvanam.com where he regularly publishes articles. We also have his book Thoughts Experiments in our library. The book Ennayum Thanneerum, which talks about the oil and natural gas, the extraction of crude oil, the politics behind the various oil extracting nations. All of that is covered in Ennayum Thanneerum. That is available in Amazon as well. He loves writing in Tamil. So at the end of the session or in between also, if there is any interlude required in Tamil, I would request you to feel free and break, because this is one webinar where you can feel free to do so. We have most of them as Tamil speaking audience. Now the floor is handed over to you. Welcome.
Thank you so much, Dr. Joshua. We appreciate your introduction and kind words, and I'm honored to see so many people having logged in. I hope you all can see my slide. So there is a lot to talk about. So I will pause maybe once in half an hour or so to take any questions, since there are a lot of people online. And feel free to ask questions in Tamil, English, or whatever you feel comfortable with. Not a problem. The purpose is not to just talk about something that doesn't make sense, but actually to convey what we are working on to every one of you, so you get a good sense of what 5G network is all about. Mrs. Rajlakshmi already mentioned, I'm part of the ACM organization. ACM is the Association for Computing Machinery. It's a worldwide organization that is promoting the ideas behind computing, the enthusiasm for code development all over the world. You can see the mission and vision posted on this slide. This is part of the Distinguished Speaker Program that is made possible by ACM. I'm grateful to the organization because of the existence. I get to come and talk to a lot of organizations and different background people like you all. So I truly appreciate the opportunity. Since I am presenting some of the Intel related material, I do have to put up this legal notice, but we'll just can move on. Just a couple of slides to give a little bit background about myself, because that will put things in context. So I studied mostly in different rural schools in Tamil Nadu during my school years. So this is my elementary school, Uthangarai Panchayat Union Aramba Padasalai, right? So I was there in the 70s, and subsequently, this is about like 2 decades back or so, I went there to see the school. We continue to do some charity work, see the children, etc. So it should give you an idea of my background. So whatever areas from which we come from, whatever our personal story is, it always manifests itself in what we do throughout our lives, right? So you can see the continuity, and we'll talk about how this connects to what I am doing today towards the end. The agenda for the talk today itself will be what is 5G. So we'll talk about the basic definition and how is it coming together. The important technological domains, meaning compared to 4G, what is different in 5G, what is changing, what is going to be considerably different, what is it going to enable going forward. Technical enablers, there are a set of technologies, concepts, notions that makes 5G possible. It's really important to understand what they are to get a good sense of what 5G is. We'll talk about business and societal implications, as the title of the talk indicates. And then we can have Q&A. As I said, we'll probably stop in between a little bit to field questions as well. This slide is to show in the overall network, where is it that we are functioning, where are we working, right? So my team's functionality is actually falling into this base station area. This basically, think of it as cell towers, right? So in the network, you basically have mobile devices. That's a smartphone that you have in your hand that connects to the cell towers. And then that goes back to the core network where everything becomes data traffic and then goes back to the data center. And of course, it's not just one linear network. And as you can imagine on this part, this becomes a large cloud where the entire internet is represented just by this data center. But this is just to give you a visual representation of the work that we are doing, where is it going, right? So as it was said in the introduction, we work on SoC, that stands for System on Chip. Those are huge integrated circuits that contain most of the functionality features that are required to run a cell tower. So if you imagine, let's say, Intel's Pentium chip, and we sell that to, let's say, something like a Dell or a HP kind of company, then they put a box around it, make a PC, then they sell that to consumers, right? Along the same model, we create what are called these SoCs, system on a chip, and then we sell this to equipment manufacturers that make equipment to run cell towers. So that would be something like Ericsson, Nokia, LG, Samsung, companies like that. Then they use this device as the core CPU of the box that they are building together. And then they sell that to the Vodafones, Reliance, AT&T, Verizons of the world who install it on the cell tower to run the business, right? So you understand where our contribution currently goes into. As you can imagine, Intel does work and sell products on all these areas. We do have chips and network cards, etc., for core network, for data center. But the work that I am doing, my team is doing, goes into these cell towers, right? So it gives you a visual representation of where we function, where we fit in. Usually, it's interesting to put this picture up, because when we say cell tower, you might usually think the kind of cell towers that you might have normally seen, but we have to make sure the chips that we put together, the software, the servers, they need to work in extreme conditions. So this is a cell tower in Sweden in like deep freeze winter time frame. And then this is a cell tower in Arizona in US that's full of desert. Often the temperature can really shoot up, right? Right now it's about 8:42 a.m. in Allentown, Pennsylvania. When I look outside the window, the temperature is about 13 degrees, 13 degrees. It's very pleasant. But the chips and the systems that are put together need to work in these extreme conditions as well. It's not going to be in air-conditioned rooms all the time, right? So it's important to keep that in mind, as it does play bring in a lot of difficulties in how things work. We have spent days, months trying to debug some issues that we could never reproduce in the lab, simply because the temperature is very different from where the issues were often being encountered, right? So it adds another level of complexity simply because of the outdoor environment where these things need to work. So having said that, let's dive into 5G itself. So I'm sure you're all hearing enough about 5G. So what is it? What is it going to bring in? What's going on? So you might have seen things like this. It's forging new industries. It's going to improve lives and disrupting business models, etc. There is a lot of marketing hype, right? So a lot of articles being written, which might make it look like just improving the speed a little bit and they're making a big deal of it. Or it could go the other way. I've seen, for example, coronavirus is brought in by 5G, or 5G towers are killing birds and people, things like that. Neither one is quite true. But since there is a lot of things that can potentially become possible because of 5G, there is also a lot of energy all around the world. So in US, the 5G deployment has started. We are starting to get service in our actual cell phones. Around the world, in places like China, Korea, etc., they're rolling out the service at full speed. So it is making a lot of things that were not possible before possible now. So there is a lot of energy that goes with it. If you look at the business analytics aspect of it, there are projections that say there will be about 3.3 zettabytes of global data traffic by the end of this year. And then there is expected to be about $1.4 trillion of spending on IoT. IoT is Internet of Things, right? I think you had one more talk, maybe day before yesterday, about that. So, of course, these are projections. Projections can go up and down. Maybe often it goes down then up. but it's better than not having any at all. So at least it gives you some sense of what's coming, where to focus, what is going to be possible. That thought process, that idea should exist in the place for us to keep making improvements and moving towards such goals. So what is 5G? If I often ask this question, most people say, yeah, we are 4G and then we have 5G. That means it's going to be faster, right? That is it. That is true, but that is only a small segment of the whole story. So 5G is a large umbrella. By that I mean it is not just for cell phone communication, but it is going to cover a whole slew of other areas that we will touch upon. It does provide higher speeds, no questions. And because of higher speeds, you have more bandwidth, and so there is greater capacity also. But beyond that, for example, the lower latency, right? That is the delay involved in like sending a packet, receiving a reply back, that sort of thing. That alone is going to make dramatic changes in what is possible. So we need to get into that. So another thing, it distributes intelligence throughout the network. What we mean by that is earlier, maybe you had earlier or even today, most of the time you have a cell phone and then you transmit something, and most of the intelligence is back at the network, in the data center, in the internet, wherever the material is stored, whatever is getting transmitted. Now in 5G, the idea is to spread that intelligence all across and put a lot more computing power close to the cell tower, close to individual homes, close to individual businesses, so that everything need not be transported all the way back through the network to the other end to get something done. Right? And it does connect, melts the worlds of wireless, cloud, and then computing. Previously, we always perceived mobile as first thing is to talk, right? So you make a phone call, you're able to talk, and then maybe you do WhatsApp or video or YouTube, something like that. But there is a lot more computing involved now in 5G. So we'll start talking about that. Again, just to keep things in a simple flow, you can think of the Gs, the generation, the 2G that came in the 90s. That is what made cellular communication possible, right? So till then, you need to have a landline to make a phone call. You got rid of that, and then you have cell phone communication. But that was it. You couldn't do far anything beyond that at that point. And then in the 2000 to 2010 kind of time frame, we had 3G, and that for the first time brought in data and the app revolution. So you started getting individual apps with which you can do ABC, right? So that wasn't possible in 2G, so that's a significant difference in 3G. But after 3G, we can say the last 10 years, like 2011 to 2020, you can think of it as the 4G timeframe. In this one, the faster data rates itself enable a lot more things that you couldn't do with 3G. Beautiful examples are Ola or Uber kind of services, right? You can't really do that with 3G because you need GPS capability, you need continuous tracking, you need to be able to instantly communicate back and forth when you make a taxi request, and for the taxi driver to look at it, for him or her to respond and come to you, and for you to see where the car is. All that was not possible in 3G because we didn't have enough data capability there, right? So 4G simply made a lot more things possible because of the faster data rate. In 5G, we are again going to go one order more. So that's not going to be simply just faster data rate alone, but that's going to make medicine, vehicle communication, industrial robotization, all kinds of things possible a lot more. So we'll again dive into it. So you can think of each 10 years as one generation. So the 2021 to 2030 is going to be the 5G timeframe, and it gets rolled out. It's not exactly defined as 2021 January 1st 5G starts or anything like that. It just falls into that kind of time frame, and it makes it easy for us to keep track of what's going on. Right? From the Intel side, we are really driving a lot of wireless standards. As we keep talking, you're going to realize, saying that it's complex is easy. Yeah, it is complex, but for every one of these devices to interwork, right? You may have an iPhone or a Android phone, or you may have like a tablet, or you may have a PC. Not only that, they all need to interwork. If you have different service providers, you may have websites, you may have streaming services, whatever it may be, they all need to interwork and interwork very efficiently, because we are expecting the data volume to go up considerably, right? So for that to work, there is enormous amount of work that goes on at the back end. So for example, this 3GPP, IEEE, these are all organizations that work on developing standards. So year after year, people have been working on putting together at the lowermost end, on the individual mobile device, how do you increase the battery time, right? So for example, the cell tower needs to know where you are. So the phone may have to wake up and then just send one ping to the cell tower and register itself. So when there is a phone call coming in, the network would know how to route the call to you, even if you're traveling at whatever 70 kilometers an hour speed on a highway, right? So you need to do that. But if you constantly keep pinging all the time, that is going to take power out of the phone, and the battery is going to drain faster. So there are ways to figure out how to do the pinging so that the network knows where you are to contact you, but do that at the least amount of time and with the least amount of information possible, so that you are not wasting too much battery power, right? So right there is a bunch of standards work that goes on. That's just one example, and then it goes all the way to the data center to see, as people are traveling, how do you make sure the video that they are downloading doesn't get interrupted when they move from one cell tower to next, and so forth, right? So there's so much work that goes on. And been continuous release of standards in 2016, 17, 18, 19, 20. It continues. There is still more work that is still going on. And it's hard. It's difficult to overemphasize the importance of standards, because this is one global network that need to interwork. If you have a phone in India, you come to US or vice versa, the phone should just seamlessly work across the network, right? So that level of compatibility, interoperability is really difficult to achieve. And so there is a lot of standardization work that goes in. So to get into the 5G technology itself, we can think of it in like 5 broad areas. You can certainly go in and then list 20 different things, or you can just say it's all fast or something. But if you think of it in these 5 broad terms, it gives you the core of what is new, what is different in 5G in an easy to understand fashion. So the first one is this massive MIMO. We'll talk about that in the next slide itself. That MIMO stands for massive input and massive output. The massive MIMO just refers to the antennas that go into cell towers. So we'll talk about that. So right there, just in the antenna design itself, there's so much work that goes on, so many patents, so many PhDs, so that itself, you can think, takes up about 20% of the R&D effort that goes into getting 5G deployed. Then the second one is cognitive radio. By this we mean the radio interface of the phone, the cell tower, the network. How do they talk to each other, right? That you can think it takes about another 1/5 of the effort that are going in. We'll see in the next slides why. And then the low latency that I mentioned before. Generally, people think if the thing is faster, it's also low latency. It's not necessarily true. If you really get into the networking detail, there are some subtle differences. So for example, you may be watching YouTube, but it can buffer for maybe 3, 4, 5 seconds and then start playing. So there may be a lot of data coming in, but it may be delayed for about 4 or 5 seconds, right? If you're just watching a video, maybe that's not a big deal. But if you're doing a video conference, if there is more than a quarter-second delay, it's not going to work out. So that is the low latency we are talking about. In 5G, you can simply think the 5, it's actually maps to 5 milliseconds. Currently, if you take your phone and go around, check what the latency is between you and the mobile network. I've done that check using my phone all around the world, and it can go up to like 172 milliseconds, something like that, like about 1/5 of a second, right? Whereas in 5G, it has to be under 5 milliseconds. And that alone is going to enable a lot of other things that we'll saw further down in the slides. Right? And then there is this notion of HD, Het, Net. HD is high definition. Het stands for heterogeneous, meaning multiple different kinds of things put together. It's not one uniform 5G equipment and network that doesn't have to worry about interworking with anybody else, right? So it's a heterogeneous network. It's a mix of 4G, 5G. They all need to interwork and still not fail in the services. So that HD, Het, Net brings in its own complexity, making it all working together takes another 20% of the effort. And then the notion of collaborative computing. So as we said previously, you may have a phone, you try to look at a website, or you ask a question, or you try to make a phone call. Most of the work actually gets done all the way back at the network in the 3G, 4G models, because the phones themselves were not that powerful. And in the network, the terminal devices were usually just cell phones, right? There weren't that much of variation in up to 4G. But when you go to 5G, there's going to be this ton of IoT, Internet of Things devices. So some are going to be extremely low powered. They can do only very limited, lot less computing than what a phone can do. So this could be as simple as, say, a trash can, right? A public trash can connected to the network. So it can just tell the system when the trash is full. So a cleaning person doesn't have to keep going there, visiting it 5 times a day to see if it's full or not. When it's full, it can let the system know. But that's not going to have a lot of power. It's going to just use one little thing to just tell when the system is full. So from there, all the way up to actual PCs or maybe a Tesla car, if you take, it has enormous computing capacity actually built in the car itself. So that's an end device, but it has a lot of computing capacity. So this collaborative computing, how much that needs to be done, how do we get it done close to the end location so that we can cut down on the latency and get a lot more done close to where the actual data is needed, right? So that alone is another massive amount of work that's going on. You can think of other variations, but if you think of these 5, if you, after the talk today, if you can remember these 5 items, massive MIMO, cognitive radio, low latency, HD, HetNet, and collaborative computing, you know what's significantly different in 5G, right? So let's dig into each one of these just a little bit. So this is massive MIMO. What do we mean by that? It's think of this as the cell tower, right? So currently, if you look at any of the cell towers that are running 4G, you may often see individual elements that look like a tube lamp or some vertical kind of thing that is transmitting the data out in the open. And there'll usually be maybe about 5-10 elements in the system to cover the entire 360 degrees. And not only that, the antennas just spew, broadcast that information, the signal at some constant rate out into the open all the time, right? So it's not really tuned, customized, it's not changing that much. And if you really look at the efficiency of the power that is used and how much is actually resulting in useful communication, you'll be stunned at how inefficient it is compared to an actual wired connection, right? So if you think of a wired connection, you send 1 volt, you send a signal from one end to the other, close to 100% is going to get to the other side, and then you are good. You can process that and go on. But you can imagine in a cell tower, you just need to like broadcast the signal at random and hope that there are people out there who will who have their cell phones and they are picking it up and using that signal. But 99.9% of that signal is just pushed into the ether, and it's not really bringing any value to it. If you really want to increase the number of end users by orders of magnitude, and you also want so much more data to flow back and forth very efficiently, that model would, the 4G model where you just randomly broadcast the signal, it's not going to be very efficient, and it's going to take way too much power to get it done. So in the massive Mimo model, there are companies that are currently testing 1024 number of antennas in one cell tower kind of thing. And there is this notion of beam forming, BEAM, beam forming. So this particular antenna unit, the element will actually, when it is talking to this cell phone, it will actually form a signal beam that is aimed at that particular device kind of thing. And as you are moving, say in a car, in a bus, or even you are walking, as you walk through, the signal from this blue one to green to red to purple, it will keep moving. And this particular element that was transmitting when you are here would stop transmitting, and then this one will take over, right? So it will keep doing that as you walk over, without you having to do anything. All that need to be completely seamless. The cell phone doesn't have to do anything phenomenal. The cell tower is going to take care of who's where, and then keep manipulating the signal, using the right element, using the right level of power to be able to talk to that individual cell phone at that level. Of course, if there are 10 phones here, the same beam can talk to 10 of them. But if there is nobody there, it doesn't have to keep spewing out so much of power into the air for no reason. Right? So that itself is a phenomenally different technology compared to 4G. And you can imagine, while it may be easier to see the value in it, making this work, perfecting the antenna design, making sure the software is able to sense, it's able to switch from A to B to C elements in the antenna, it's extremely complicated, right? So there is, you can think about 20% of the effort or 1/5 of the effort involved goes right into that. The next one is cognitive radio. What do we mean by that? Is in addition to the massive MIMO type of thing, the radio itself becomes much more intelligent. There is a lot more capacity, a lot more software thrown in that makes it a lot more efficient. So one thing is there are so many spectrums that are available in the system. In the 3G, 4G timeframe, the spectrums are not being used very efficiently. Not because people didn't think of it, but at that time there was no need to actually gather all the spectrums that are available because there wasn't that much of data exchanges going on anyway. But now, when we have so many more devices getting added, you need a lot more spectrum space to support all the communication that need to go on. So there are efforts going on to figure out, let's say there is a frequency band that's allocated for military's use, right? Currently, we don't touch it at all. We just say, oh, that's military band, so we can't use it, right? But if you really think about it, if you are in Trichy, there is not a lot of military operation going on that requires that entire bandwidth to be left all alone. Maybe if you are in Kashmir, yes. In Trichy, no. So why waste that military bandwidth altogether, even in Trichy? That question is getting answered where the cognition, the improved intelligence in the radio would make use of those free spectrums that are available in any given airspace, taking into consideration if there is military in the work, right? And similarly, there are TV spectrums. If there is no TV stations, maybe all those spectrums could also be used. There's the 4G spectrum, the GSM spectrum, any of these. So if things are left unused, 5G can grab it and then put that to good use. and then unlicensed and licensed users. So previously, all the spectrums need to be licensed, and only in those frequencies operators can work on, phones will work on, and so forth. But now there is an effort to unlicense, open up some frequencies where you do whatever you want. Why would you want to do that? This allows something like, let's say you have a huge corporation, a manufacturing facility that has 200 machines, right? They all need to be synchronized and need to work on something. Then Nano Industries, if there is one such functionality, you can set up a 5G tower or even equipment within the manufacturing floor to control all those equipment. And you don't need to go and get separate license as a 5G operator or anything like that. You can use the unlicensed spectrum and just go with it, right? It makes things easier. And then there is this notion of spectrum broker. As we said, if there is a lot of unused spectrum that you want to use, then there has to be a brokerage thing. So there has to be entities, software, hardware, that will negotiate and tell you, in this GPS coordinates, in this domain, you can use this, but not that. Or if you are doing only voice communication, you need only this much bandwidth, so you don't have a need for a lot of bandwidth. But if you're going to do a lot of video conferencing and video transfer, high quality video transfer, then you need more spectrum capacity. So there are the spectrum broker models that are coming in that will sense and see what spectrum is free, what is your capacity, so how much can additional capacity be added, right? And then the software defined radio, which means earlier, if you think of radio, you might be thinking of a hardware block that is just broadcasting something, receiving something, right? Old-time walkie-talkie kind of thing. But if you are going to keep switching between spectrum, if you need to negotiate with the spectrum broker on the network to see which frequency you can pick up, etc., you need a lot more software that will interface with such entities and then be able to switch from frequency A to B to C depending upon what is going on and what the requirements are. So all this, again, you can see the amount of work involved in getting all this come together, work seamlessly without the end user having to worry too much about it, right? So it's a massive effort that is going on. If fully, completely, nicely deployed, we want to see this kind of a model where the entire society is sort of carpeted with different kinds of radio signals, but a device that is moving from point A to B to C can seamlessly switch from one kind of technology to another without any interruption perceived by the user. So if you can think of this, an entrance base station, meaning this is a huge cell tower and you have a massive antenna with 1024 element, all that, great. And this can transmit all over here, but maybe there is a small hilly area, like a lot of tall skyscrapers sitting around here, and so a device that is here is not able to see this cell tower. Right? In that scenario, each one of these buildings will have its own repeater station kind of thing. And you can see it's not only on skyscrapers, it is portrayed on each one of the lamp posts in the street, right? So you can have a solar panel and a small tower here. And so this can pick up the signal and then provide coverage right there. And not only that, on top of that, even individual homes with the user permission can receive a signal and then allow that local Wi-Fi signal to be opened up without say this user being able to hack into your home network, but on a separate frequency. You can get the signal and then broadcast it here, so you continue to have Wi-Fi signal here, right? Even though you can't see this massive tower continuously. So you can see different spectrums, different technology, Wi-Fi, not Wi-Fi, GSM, all interworking together to provide continuous coverage in whatever hidden area, open area you are in. Right, and these are all the different spectrums that we work on. So in USA, there is XYZ, Europe, Asia, Pacific, India is all falling into this region. So there is a lot of negotiation going on. hey, can we narrow the spectrum so this can still be allocated for this, and can we take over the spectrum? And that negotiation is going on. This is to open up a lot more transmission space to accommodate all the things that are coming in. And then we mentioned collaborative computing. So I gave an example of a trash can with a little chip, and then a Tesla car. The Tesla car has so much of computing capacity, whereas the trash can doesn't. But we want to bring them all in. So the notion of the data center being a massive center somewhere else, and then your phone always being a weak computing node in the overall network, that goes away, right? So you can get the computing done at different locations. So it's expanding across devices and relays. So again, how much can you do? What can a car communicate to the network? I mean, we can talk about just car communication alone for an hour, right? So do we let like a car to talk to another car? Do we want the car to only talk to the cell tower? What if the cell tower is not accessible? Does the self-driving car still drive? How does it drive? And what can it talk to the traffic lights and so on and so forth, right? So there is so many possibilities in collaborative computing. And then we talked about, mentioned this high density heterogeneous network. By this we mean you cannot simply erase all the network that is out there, 4G network or anything else, but you need to bring in 5G, make it work on its own, but also interwork with all the other technology that's there, right? So it's going to be high density, but it's going to be heterogeneous. So the things need to interwork. It needs to work within a building, in a manufacturing floor, from a cell tower as a standard things go, or in even newer model, right? So we'll see one or two videos right after this. Okay, we are there right on cue. Let me play one video. This is Nokia is one of Intel's customer. So I wanted to give an idea of a base station. Whenever I say base station, think of a cell tower, right? So whenever we say cell tower, we always think of a huge tower that is mounted on the road, on the side of a road as you are driving away. But there are new notions of base stations that are coming in. So the idea is, let's say there is a A.R. Rahman concert that is taking place in Trichy on a remote location, right? Because there's going to be like 1 lakh people coming in to listen to the concert, but they are going to be there just for that one day. But when they come there, they all want extraordinarily good cell tower capacity. For that, you cannot go and install a huge base station. It's too much capacity. But 2 days later, there is not going to be anybody there anymore, right? Once the concert is over. So how do you support such scenarios? So Nokia is trying to answer that with this model. Let me try to share the video. Hopefully it will come through properly. It will give you a break. Stop listening to me. Go here. Don't comment. Make it full. Option, then no back tab. Okay, can someone confirm that you can see the Nokia Bell Labs video?
Yes.
Okay,
Yes.
all right, I'm going to play the video. Okay, that was just one. So the idea is, you can hear my voice again, right? Oh, so in this case, you can see it doesn't require power because it's driven by solar panel. It can get connectivity from some other antenna somewhere else, and then it can provide signal just locally. And once it's over, I mean, you can see it's not even like two people are going and installing. You can just put it on a drone, just drop it wherever you want. And once the event is over, you can just pick them all up and walk away, right? So this kind of instantaneous improving in capacity and then dropping it down, making it extremely flexible, that is one. And then this is another video. Let me try to share it.
Hi, this is Ebrahim Bushari from Lime Microsystems. There has been a lot of talk about small cell base station in recent years. We decided to take a design that is based on our first generation chip together with an Intel baseband solution. And this platform has been designed and implemented by one of our partners, Cambridge Consultants. And it's compact, low power, to the extent that we can install this on top of drones and have a flying network. These could have use cases in emergencies, in disaster areas, or developing world or rural areas.
Hello, I'm Danny Webster, Principal RF Design Engineer at Lime Microsystems, and this is a Ubuntu drone with a fully operational base station on top of us, and we're now going to try and make a call. Hello Ricardo, good weather.
There we have it. We are making calls through our own drone-based network.
Let me go back to my slides. Okay, so I mean, those two just gives you some idea, right? So it can actually be deployed by a drone, and then you can just go put it somewhere. That becomes a stationary, temporary cell tower. Or you can even mount it on a drone and then keep flying it around. So why would you want to do that? Maybe there is a fire that's going on, or there is a disaster. You still want to provide some kind of connectivity, so there is no nice place to go put it in. It still functions, right? So these are all different variations that are being worked on currently. So let's. We went through those 5 items, right? So there are a lot of technological enablers within that. So we talked about antenna technologies, specifically the 1024 element massive Mimo, standards work that are going on. There is millimeter wave. By this we mean there are some really high bandwidth frequencies that are available. When we say high bandwidth, you can use those frequencies to send a lot of information very quickly, right? So in like gigabit kind of range. Why is that needed? The system, the network can perceive you traveling in a bus at 70 kilometers an hour speed. And as you go through some parts where you have this millimeter wave antennas installed, if you are watching a movie as you are traveling in a bus, it can dump a whole bunch of content onto your phone or the mobile device quickly. So you will continue to see that because the network knows in the direction in which you are traveling, for the next 2 minutes, there may not be a good cell tower coverage, right? So you can use these kind of high capacity systems to dump a lot of information onto your device and continue. Somebody raised their hand, so maybe I'll stop here to take a couple of questions before going further. Is there a question?
Yeah, there's one which has been typed by Mrs. Tenmuri. She has asked, will there be any radiation affecting?
Sure,
Thanks
yeah.
to all these Tamil movies, we are very worried about 5G radiation.
Absolutely, yeah, that's a good question. Yeah, I've got the chat one enabled, so hopefully I can see additional questions. The European agencies are particularly sensitive to that, I would say, even more than US. So in the conferences that I've been attending, there is a lot more work being done in Europe to assess the seriousness of radiation, right? So far, I have not come across anything that's particularly worrisome. I would be perfectly comfortable with my children carrying around 5G phones and using it. And I do have one, and I don't have any problem. But it's not like a general blanket statement, brushing it aside or poo-pooing the whole thing. There is serious work that is getting done. So particularly, there are labs in Europe that is individually testing different frequency, what's the signal strength, how high the tower should be, if something is going to be on a lamppost level, what frequencies are appropriate to use in that range, etc. So this overall kind of WhatsApp messaging of 5G is coming to kill the entire world, 5G is spreading out corona, those kinds of things, I don't see any like real value or merit in any of those claims. There are simple things like, if you think the map of corona, where it is happening is actually mapping to 5G, they are all correlation and not causation, right? So that's a big thing in statistics. They'll keep beating that into your head if you take a statistics class. Wherever there is a lot of people, you end up getting 5G services, because that's where service providers can make money. And because of the people density, you're also going to see more corona infection, things like that. So it was kind of disappointing to see the correlations being presented as causation, but it's really difficult to convince people if they're really pushed into that realm. No point just ridiculing them. You need to really sit down and talk and address their concern. And of course, research need to continue so that any long-term effect that need to be monitored is not brushed aside casually. Right? So this 5G NR stands for new radio. So we talked about that. The movable base stations, we talked about that. MEC stands for mobile edge computing. That's the one that I've been saying. So the idea is to move a lot of computing close to the edge. By edge, we mean where the cell phones or the mobile devices are. That is to bring down the latency, right? So to make
there is one.
Sure, yeah, I see one more.
Sorry, one more question is there, and one Yoga Chandran also has raised his hand. The question is, the Nokia HD HetNet is like MAN or expanded hotspot, sir?
It's more like expanded hotspot, but some of these definitions are more for our understanding, right? So if the technology work, will come up with some new name, but I currently put that more on the expanded hotspot side.
Okay, and Mr. Yogeshwaran? Somebody had raised his hand. Unmute and you can ask your question.
Okay, that's fine. We'll continue. So MEC stands for this mobile edge computing. As we said, that's to bring down latency. This SDN, NFV, you might have heard these terms if you are in the IT. If you're not, don't worry about it. This is software-defined networking and networking functional virtualization, etc. What this means is similar to that mobile edge computing, something that needs to be done usually at the back of the network. Initially, you didn't even think such things are possible to do close to the edge. Now you can move all that out, right? So for example, simply think of, let's say, a website. Years back, we used to think, oh, a website means like serious computing. You need to have a big server sitting in some place. Right now, you can run a web server simply on like a $4 board computer called like Arduino or Raspberry Pi, if you've heard of those. Or any of the cars, they all have web interfaces for you to touch and do stuff, right? So it's not that difficult. So it's something that needs to be done. If it can be moved closer and closer, that makes things much more responsive, cuts down the latency for the end user. So it could be as simple as, let's say you are typing something on WhatsApp, the spelling correction or suggestion as to what you want to type next. Does it have to go all the way back to the network, to the WhatsApp server in another continent? Or can we bring it closer and closer to the cell tower? Or maybe you can just, there's enough memory and capacity available in the phone itself. So you can potentially put that in the phone so it actually works like a local computer. So that's going to cut down. You're not going to see a lot of some other computer was making noise. So that is to keep moving all that network functional virtualization, meaning what was happening way back in the network, how do you keep moving it towards the end user, right? So that's the idea. This URLLC stands for ultra reliable, meaning you want like 5969 uptime. It should 99.9999% of the time, it should never go down, ultra reliable. Low latency communication, right? So the latency need to be brought down more and more. Why do we keep talking about low latency all the time? That's because if you are simply doing a phone conversation, the bandwidth requirement is too small, right? So you can find your way to the other end and then bring the signal back and it's all good. But if you're really doing a huge high definition video conference, you need a lot of bandwidth that needs to go back and forth between the two ends. And for that, you need this ultra reliable low latency communication. Otherwise, you're going to see buffering. If you're going to have like a virtual reality goggle and then you're playing games, the latency is more than, let's say, 200 milliseconds. You're going to feel what they call seasickness, meaning you move your head and the picture is not moving fast enough, right? So that's going to make you feel like your eyes are not working right, kind of thing, and human beings can't handle that. So if such things need to come through, this URLLC becomes extremely important. These are again abbreviation just to say machine-to-machine communication, etc. So these are all technological enablers that we kind of covered on the 5 big areas that we were talking about. Right. Let's switch into another video. Hopefully you'll enjoy. This is to show the effect of low latency, right? Let me not say more, so let me just play the video and you'll probably enjoy this. I'm going to take this here, make it full screen. This is a slightly longer video, but it should be fun to
Hey, I'm Bill Goodman, lead engineer from the Ericsson technology team.
And I'm Dan Huffman, principal engineer for Verizon Wireless.
Our goal today is to push the limits of mobile 5G. We're fundamentally advancing the technology that wireless consumers will use in the next decade and beyond.
Speed is key. We know we have to deliver the fastest 5G connection possible. Today, we're out here at the Indianapolis Motor Speedway to test our newest technology inside of a moving vehicle.
We're pushing beyond today's technology. With multi-gigabit speeds and super low latency, we're enabling new applications and the Internet of Things.
As our vehicles get smarter, our network also has to get smarter. And we're doing exactly that with a 5G network capable of pinpointing your device and maximizing your bandwidth at all times.
We're going to have some fun today.
But remember, all the results you see today are real.
Bill, you got a copy? Copy, Control. We're ready for our run. Let's do one for real. Whoa! What's wrong?
Copy that. Throughput looks great. Go ahead and start the downlink stream. The downlink stream looks great. Go ahead and start the uplink. All right, guys. We ready for the final test? Okay, driver. Bring it back to the blackout test. Blackout test?
I don't remember any blackout test. To really kind of push the envelope and showcase the low latency, we added in this virtual reality driving where we'll black out the windows, virtual reality glasses will be worn by the driver, and the camera will take a feed and uplink through 5G into the network, turn around, send it back down over 5G, and do that quickly enough so that the driver can react appropriately as he's running around this track at speed.
I think it's safe to say both Verizon and Ericsson are very happy with the results we were able to achieve today. We were able to prove in a highly mobile environment that we could exceed speeds in excess of 6 gigabit down, all while maintaining extremely low latency.
We took a great step forward today, Dan. 5G is the future, and today the game changed. Next time you're in the car.
Let me go back to the slides.
So there is a question which says, is there any limitation or instructions about the distance between the HT hitnets, sir?
Of course, I'll cover that in the next couple of slides. So basically, it boils down to the speed of light, right? So you cannot go beyond the speed of light. And so that's what puts what the limits are. So let me continue. You will see that in the next couple of slides. Can you see the, actually it's still launching. Okay, should be able to see the slide now?
Yes.
Okay, all right, okay. Again, in the previous slide, one may ask, why do you want to like blacken your own windshield and then drive around? It's just for dramatization, right? So the idea is that you are able to mount a camera that is seeing what's going on and then send it back to the cell tower, and it's beaming it back to the VR goggles. And that's happening in such a low latency that this is where the latency aspect can be demonstrated well, right? So it's not enough just to have a big pipe where a lot of data can come in, but the latency should be really, really low for the driver to be able to see that practically in real time so that it doesn't go crash into something else. That's the point that was being made there. We'll talk about that in a minute in another slide. So the multi-access edge computing, so we talked about this already. So this is to move the applications that are in the core of the network, keep moving it to the mobile edge computing servers that are close to the cell tower, and then see how much can be done here itself, right? So a good example is what we said 10, 20 years back, the phone may not be powerful enough to provide corrections to your WhatsApp message or grammar or suggestions as to what to write next. You may not have had that much capacity at this end, but now you do. So if you move that over here, then of course you get much more interactive, faster response user experience that makes it more pleasant to use. And of course, everything comes with a cost. If you keep doing that a lot, then you're going to drain the battery faster. That's why I was saying initially, a lot of work that goes into extending the battery life as well. So you need to hit the balance on most of it. And there is, as originally my introduction said, my team is specifically working on optimizing a lot of this. So when you write code, if you keep putting like if then else, that's all going to take a lot of time and effort, right? So how can you compile? How can you make it much more optimized? How can you fetch some cache ahead of time? How can you get this data located in the same cluster of code so that it doesn't take too long for it to go fetch it from somewhere else? That level of optimization at the machine instruction level, that keeps cutting down the computing power needed, the time needed, the battery capacity that's needed, so the user experience can get better and better. Very recently, like just less than a year back, there was this release 16 that came out. So some of the big things that came out of that is this V2x communication. V stands for vehicle. So it's from car to anything, right? So if you have a car that has a radar, it has a camera, maybe it can gather a lot of information and then send it to the cell tower. So it can make sure the traffic is flowing smoothly. There are plans to, for example, remove most of the traffic lamps once the car becomes more and more self-driving. And if you can really do that, I mean, most of our current infrastructure is designed to accommodate the limitations of human beings, right? What's our reflex time in reacting to a situation? How much time do we need to cross an intersection? Things like that. We can't just let one driver go this way, another driver go this way, second after second. So we have the current model of traffic lights where you have a green signal here and red here, and then you let a lot of cars go this way, and then put red here and then green here to let a lot of cars go this way. But in ideal scenario, that actually Intel is really big into self-driving technology also. So there are tests that are going on where you can remove all the traffic lights and just guide the car. So as it comes in, there is another car coming in this way. You can slow this car down and let this go, and in the next second, this can cross the intersection, and that can increase the efficiency of the intersection, meaning a lot more cars can cross the location, and that can cut down the amount of traffic congestion, right? So there are all these things going on, and the vehicles can talk to the cell tower, they can talk to each other, they can talk to your phone. So that V2x communication is a new aspect that came out. Side linking, which means instead of just you talking to the cell tower, I mean the mobile network being the main thing that is controlling everything, are you able to just talk to each other? So maybe one mobile device to another mobile device, one car to another car, without having to bother the network at all. So that is ongoing. Private networks, we said that a good example could be in a huge manufacturing facility, you have a network within that manufacturing floor itself, right? And location services, this is GPS kind of thing that is increasing considerably. And then extended reality. The extended reality is a very interesting thing. We'll talk about that in the next slide, where now there are robotics-based surgeries that are being attempted. So the doctor can wear a virtual reality goggle and then conduct a surgery, and the remote location robot can simply repeat what the physician, the surgeon is doing to actually conduct the surgery. You can go up and look up this system called Davinci. They are one of the pioneers, and the systems are currently working, but you can imagine how reliable the network need to be. Halfway through the surgery, you can't say there is no network connectivity, right? So that's what's coming to. I do want to talk about what are the major stumbling blocks, right? So we are talking about all these glorifying great technology. Is it all hunky-dory, everything going great? Not necessarily. So one thing is nobody wants to pay for it, right? I don't know if you all realize it, but the success of the IT technology, particularly companies like what Intel did in like being able to pack more and more transistors while keeping the cost the same, the Moore's law kind of thing, that has trained the entire world to expect better and better technology for the same price or even less price. Right? So I'm sure you all realize the kind of phone that we had in the 90s and what we have now. Today's is much, much better. But if you take the inflation aspect out, we are actually getting it for a lot cheaper than what we were paying then. I am not sure if you really see that in any other domain in the world, right? So I'd like to quote this one example in the pharmaceutical industry. So hepatitis C is an infection that can eventually affect your liver. It can be very serious and so forth. So there is a company called Heterogeneous that has come up with a drug for it. It's not a surgery, it's nothing big. You just get a set of pills. You take one pill a day for 40 days or so, and then the infection goes away, right? The price for that treatment for that one person, Hep C, is $100,000 US dollars for one person, right? And they say that you should not look at just the price of the pill, but if the patient goes through a really serious liver failure, how much money one will be spending. So they should get a share of that, and so the price is justified. Right? You can go look it up. R1E is the company, Hep C is the issue. It's $100,000 for one person, and it's just like simple pills, right? It's not like a very complicated procedure they need to do. If you think that is well deserving, great. But if you say for all this 5G technology that we are talking about, instead of whatever you are paying per month, 500 rupees, if you need to pay 1,000 rupees for a new cell service, we generally say no. Even probably I would say no, because I want all this technology, but I want it at the same price. Right? So nobody wants to pay for it. So how do you do that? And then it's not a simple one technology upgrade. Right? You can see so much need to be deployed, so much need to interwork, so much need to be proven. So it's not like you just update some few cell towers and it's all done, right? So there are a lot more, but how do we solve these issues first? So one idea that is floating around the industry is to come up with network slicing. I won't get into too much detail, but the idea is to create different channels within the network, and then provide a premier channel where, for example, hospitals are using it to do robotic surgery. You want extreme reliability, you don't want things to fail, etc. You pay a premium for it, right? Compared to that, another level where you have voice call, you want good reliability, but it's not as important as the surgery network. And then a third level where you may have, just web surfing or watching YouTube. You want a lot of bandwidth, but once in a while, if there is 1 or 2 seconds buffering delay, it's maybe not a big deal, right? Of course, this makes the network net neutrality issue. It brings it front and center, because the notion of net neutrality is to provide equal access to all the different services. But if we keep doing that, that actually becomes something like somebody surfing the web, looking at some movie news, their network access has the same priority as an ongoing surgery. That doesn't really work out well, right? And so you do need to, this is a notion that's coming in. Maybe with the 5G, with so much of bandwidth available, you don't really need to worry too much about these prioritization. But this is one approach where you can slice the network and then charge a premium for higher capacity, higher reliability, and then offer a lower tier where the price is cheaper. Right? And this is the one that answers the question about the limitations. So if you generally look at the speed of light, right? So 1 millisecond latency is what is needed for manufacturing applications. By that we mean within a millisecond, a machine, a lathe, a milling machine, something that's drilling, that's cutting, doing something, a CNC, need to be able to keep talking to the system so that it's not cutting too much, not cutting too less, etc. But 5 millisecond latency is good enough for remote surgery through haptic net. By that we mean when the surgeon, let's say, makes an incision with a scalpel, that's transmitted to the other side, the robot does it, and that feedback is given back to the surgeon, so he or she can actually feel the feel of the flesh getting cut, kind of thing. So that needs to be within the 5 millisecond kind of latency. If it goes beyond that, it's not going to work. So the speed of light is 300 kilometers per millisecond. So this has to be a round trip, right? So you make a move and the robot does it, and then it needs to come back. So that round trip reduces it to about 150 kilometer radius. If you allow 5 millisecond latency, that means about 750 kilometer radius, or about 450, 460 miles. Right? So that means a surgeon can sit in one location and then can perform surgeries in the 750 kilometer radius without compromising the quality. So that kind of answers the kind of limitation that we need to deal with. If you ask, why do we want to do this remotely? Why can't the surgeon go there, or shouldn't we be training more surgeons? Absolutely, that's a right question. But the thing is, there can be situations where maybe there is a fire, maybe there is a flood, maybe there are not enough surgeons in a ward zone or anything like that. In those scenarios, these technologies can come in to complement the standard care that's provided through a physical surgeon being present there all the time. And the 10 millisecond for VR applications, so like what we saw in that race driver driving around, if there is a 10 millisecond gap, it's okay. But beyond that, it's going to look like you're not seeing it in live, right? So it needs to be lower than that. And this strict net neutrality will impede that ultra-reliable, low-latency applications, but we need to figure out what's the thing. So the solutions could be isolated network. So of course, you can have a separate network provided by the service provider for hospitals alone. They charge a lot of money, ensure reliability. That's not the standard internet. So that kind of thing is one approach. Our private network that we talked about, so there are separate frequencies. The companies themselves set up their own network and manage. That's not mixed up with the internet, cannot be hacked, cannot be connected, and so forth. We need to go with the layered approach where you pay a premium to get reliability, and then you get what's left. That's best of effort service at the lower level where we don't care. So that's basically more efficient spectrum use. That means you need less spectrum. Then you can share the spectrum, and that increases the dollar generation for the service provider, right? So we talked about these three. Then there are even these additional ones: Greenfield versus Brownfield. Meaning, Greenfield is a fresh country. Let's say some country in Africa that doesn't have any cell phone network at all, and then you suddenly go in. Yeah, you can deploy 5G fresh because there is nothing else that it needs to work on. This is something like India, where the mobile network just took off when it came in the 90s because the landline network was not that great, right? Whereas in US, the landline network was really good in the 90s. So even I myself, I didn't rush out to get a cell phone for a long time because we had phone everywhere and it worked fine, right? But if you already have a system, making a new system come in and work becomes difficult. So that's a brownfield issue. It's not a greenfield, it's a brownfield, meaning there is already stuff there. You need to make it all interwork properly. Many deployment use cases will require social acceptance. If you get a chance, the book Mrs. Rajalakshmi mentioned, please do read that, and you can also go read it on the Solvanam website in Tamil. There are a lot of dilemmas that need to be sorted out. So if there is a self-driving car that goes in, we can talk about thought experiments for another hour. Simply saying, if there is a pedestrian coming in, should the car just brake really hard, even though that's going to knock the teeth out of the driver and the passenger in the car to protect the pedestrian? Or if the pedestrian is crossing it illegally, is it okay to hit the pedestrian to protect the car driver? Those kinds of things. Currently, these questions are answered by the reflex, how fast people respond. But if it's self-driving car, the societies need to answer these kinds of questions, right? So there's a lot to go there. So ethical concerns need to be sorted out. So this is my kind of last slide. So throughout the last couple of years, I've been going around demonstrating an SoC, the system on a chip, device called Snow Ridge that goes into cell towers. So we made like a mock-up of a cell tower equipment inside with our box bus, and we were demonstrating all that. And this is a picture from Barcelona, where there was a Mobile World Congress that was going on. That was our previous CEO giving a press interview and so forth. The reason I'm showing this is I was actually standing on behind this podium on this side. An engineer from Poland, an elderly man, came by, and then I was giving him this big pitch about our device, it's doing XYZ. He heard all that, and he was saying, I'm looking around all this glitz and glamour, right? So are we really helping humanity? So how does it help humanity in the end, right? That was his question. That sort of rang a bell in my mind, probably because of my own, where I came from sort of thing. So let me show you one last video, and then you can close it out. Let me stop sharing and start sharing again so that I can share the audio.
India is all about bazaars, these small mom and pop stores. We thought about starting chapters to bring all of these bazaars online.
Handicrafts are a part of my tradition. When I started my business, the middleman would take all the credit. That's when I decided to put my name on the products.
The time had come to build a large company, but it took way longer. And then Geo came in, and then it just took off.
I now have a Geo phone. My products are sold in 20 countries outside of India.
Suddenly, women have access to their own device. 20% of our 600,000 merchants used to be women. Now, about 40% is women.
My dream is that the daughters in my community match stride for stride and walk shoulder to shoulder with the rest of the world.
Between a dream for India and a new reality, there's a bridge. Cisco, the bridge to possible.
The commercial was running right in front of me, so I was using that. And of course, you can say all the 3-4 videos I saw, I showed, they're all just corporate commercials, and isn't it the same thing? Does it really justify, etc.? But like every technology, everything that we are doing, there can always be positive and negative things in there. Right? So as technologists, as educators, as people involved in this domain, you do need to make sure things are moving in the right direction. And if you do, there is enormous potential in what can this achieve. Right? That's my last slide. Thank you all for hanging around. If you have any question, I'd be happy to answer.
Thank you so much. I would request the participants to voice their questions, unmute yourself. And as told in the beginning, you can feel free to question in Tamil also, because we have the entire audience, and as a homogeneous community, all of us understand Tamil here. Yes.
Absolutely. முன்னாடியே சொன்ன மாதிரி the purpose வந்து தெரிஞ்சதெல்லாம் சொல்லிட்டு வளர்ந்து போறதுக்காக இல்ல. Correctly, we need to get that conveyed, right? So please ask anything you may have.
Any questions?
If not, thanks for the opportunity, and go do read all the stuff that I've been writing about. I think from an engineering perspective, I mean, as I said, I grew up in like small towns, and I didn't know what I should even read, right? So whatever exposure I get, அது எல்லாத்தையும் தமிழ்லாம் எழுதி இதுல போட்டு எல்லாரையும் படிங்கன்னு கெஞ்சிட்டு இருக்கேன். So if you want to read it, that makes me happy. So.
Yes. To add, he has been named as one of the top 10 writers who can write in Tamil. அதாவது தமிழ்ல எழுதுற எழுத்தாளர்கள்ல சுஜாதா மாதிரி எழுதுறார் அப்படின்னு சொல்லி one of the magazines has given him the credit. So அந்த தமிழ்ல படிக்கும் போதுதான் நம்மளுக்கு அதை பத்தின ஒரு அது எவ்வளவு இன்ட்ரெஸ்டிங்கா இருக்கு அப்படிங்கறத நீங்க சொல்ல முடியும். So solvanam.comல வந்து most of the writings on இப்போ ரீசெண்டா வந்த ஆர்டிகல்ஸ் எல்லாம் it is about COVID and எப்படி நம்ம அந்த vaccines பண்ணிருக்காங்க, அந்த வேக்சினோட effectiveness பத்தி எழுதியிருக்காரு. I think that is the last, right? Or you've written something after that.
அதுக்கப்புறம் பரோபகாரம் அப்படின்ட்டு philanthropy பத்தி I was writing a 5-part series. So I try to write philanthropy or oil and gas or computer processing. If you just choose my name, all those things should list out. So please do read, ask your students to read. I'm hoping younger generation also will benefit from it.
Okay, so it is silvanam.com. I'm repeating it again here. So if there are no questions further, then I think I'll hand over the session to Dr. Joshua for the vote of thanks. Yes, thank you so much. The speaker has shared his link on Solvanam website, and I see a lot of positive comments about the presentation as well. I think you must have seen that. As well. Thank you so much.
Great. Thank you all. Bye-bye.
Yeah, thanks. Yeah. Bye.
Thank you, sir.
Thank you.